Okay, I'm going to go through some momentum and impulse questions for our finishing up this last unit. So let's start with conservation of momentum. Sorry, trying to get myself situated here. Okay, what is conservation of momentum? Remember when we studied energy, we talked about conservation of energy. Momentum is another one of those things in nature that is conserved in certain situations. And conserve means before and after an event happens, the momentum total stays the same. That doesn't mean that the individual momentums always stay the same. So let's say we've got we'll just have two balls, okay? So they're going to run into each other. One's traveling in this direction, one's traveling in this direction. Let's say this one has a momentum of 1. This one has a momentum of -1. Remember, momentum is a vector because it's mass times velocity, and velocity is a vector. So it can have a negative sign, which indicates the direction. These are in opposite directions. So I've got one that's positive, one that's negative. They're going to run into each other, bam. And then when they move apart afterwards, now they're going to be moving in opposite directions. Okay, so now this one is going to have a momentum of -1. This one's going to have a momentum of 1. But the total momentum of this whole system of objects, and when we say system, we just mean two or more objects, the total momentum is still the same. 1 minus 1 is the same as, again, 1 minus 1 here. In order for momentum to be conserved, you have to have what we call a closed system. And that just means that no external forces are acting on the objects. So as long as my two balls here are the only things interacting with each other, there's nothing else. There's nobody giving them a push, or there's no friction on the surface, then they've got a momentum before they collide, and that's going to be equal to their momentum after they collide. That is what conservation of momentum means. It means that your total momentum stays the same before and after the event. And we usually talk about collisions in momentum just because that's an easy way to look at conservation type scenarios. Okay, we've got a bowling ball with 25 kilogram times meters per second of momentum, and it's going to hit a bowling pin that is at rest. And then afterwards, the ball has 5 kilograms times meters per second of momentum, and the pin has 20. So we're going to compare the change in momentum for each object, and we're going to look at the total of the system. So I'm going to move to the back because I don't leave enough room there. So we're going to start off, we've got a bowling ball, and it's got a momentum of 25. And then we've got a pin, and I'm sorry, I am bad at drawing. It is at rest because it's just sitting there. So it's got a momentum of 0. So my total momentum is going to be 25 plus 0. Okay. So this is before, and it's helpful to draw pictures like this a lot of times so you can see what's happening. Then the bowling ball is going to hit the pin, bam, and after, so now my pin is going to be moving because my ball hit it, and it's going to cause it to move. My ball is still moving, but it's going to slow down because it hit the pin. So let's go back to the front. We've got 5 for the momentum of the ball and 20 for the momentum of the pin. Okay. So if I look at my total, now it's 20 plus 5. It's still 25. So my total didn't change. My objects changed momentum, though, individually. So the ball had a momentum of 25. Actually, let me do final minus initial. So the ball has a final momentum of 5, an initial of 25, which gives it minus 20. So it actually lost momentum when it hit the pin. And then the pin had a momentum final of 20, started off at 0 because it was at rest. So it gained 20. So individually, the ball lost momentum when it hit the pin because it really gave some of its momentum to the pin, in effect. And then the pin gained momentum because it was at rest and now it's moving. But my total stays the same. So what's my change in momentum for each object? It's the same value, opposite direction, basically. So the ball lost basically 20 kilograms times meters per second of momentum, and the pin gained 20. And then did the total momentum of the system change? No, it stayed the same. All right, then we've got 2 collisions where we've got an egg. It's traveling at 15 meters per second, and then it hits the ground and comes to a stop. And then we've got another egg that hits a pillow and comes to a stop. Okay. So in both cases, if we look at our change in momentum, so that's just my mass times my change in velocity. In both cases, it's the same egg, so it's got the same mass. My velocity started at 15, so my initial is 15. So I've got 0.1 times, and then my final is 0 because it says comes to a stop in both cases. So 0 minus 15. And that's the same for both cases. So it's the same change in momentum for both of my eggs, because they both started at the same velocity and then they're both coming to a stop. So let's get my handy dandy calculator out. Ooh, what happened? Okay. So I've got 0.1 times 15 gives me 1.5. That's minus. So that's my change in momentum, and that's the same for both. My impulse, remember we talked about in class, impulse equals change in momentum. If I apply a force over a time to an object and I change its velocity, then those are the same thing. They're equal to the same thing. So the impulse experienced by egg A and egg B is going to be the same. Okay. How about the force and duration of force? So when we are hitting the bare ground, that is going to be a large force because that's hard. You don't have any give there. And it's going to be a short time. So imagine an egg hitting the ground like bam. Okay. So egg A has a large force and a shorter time that make up its impulse value. Egg B is going to have a weaker force because it's hitting a pillow. And then it's going to be a longer time because it's got some smush in that pillow, so it's going to interact with it for a longer time. So our egg A scenario, we've got a large force times a smaller time. And then our egg B scenario, we've got a smaller force over a longer time. Okay, I'm kind of running out of time in this video, so I'll do another video for these last two problems.